Take it away.
All right. Next, we have Ujjwal Lanjewar. He's a veteran of storage industry with more than 18 years development and distributed file system products. Ujjwal has also architected, developed technologies around NAS, such as global namespace with federated FS caching solutions, file data protection with replication, etc. He's relatively new in the Lustre world and catching up with an objective of making Lustre more relevant to newer HPC use cases. Ujjwal works with Seagate Technology in India, and he's currently designing high-performance HSM solution. Ladies and gentlemen, Ujjwal.
Thanks, Steve. Good evening. So we have had a series of HSM presentations. So this calls for probably a HSM day in the next LUG. Okay, so this talk is around Lustre HSM, particularly about the high-performance distributed data mover, which is mostly designed, to cater to HPC use cases. Now this, I safely assume that we all have some background about Lustre HSM, but thanks, John, for giving a good overview on Lustre HSM. So that makes my job easy. Okay, so agenda is we'll start with a quick overview on the current state of the Lustre HSM. Essentially to just take a note of a few important points that forms the basis or base for the discussion today. We'll take a look at the development environment or target environment just to establish a context and give a background on the kind of problem that we are solving. We'll then spend some time on the overview and architecture of the HSM solution, essentially the distributed data mover, which is the primary component. And then finally, I'll talk about some of the challenges that we came across with our development so far, and then talk about some of the proposed solution as mostly a wish list for Lustre. Okay, so this is just a quick highlight on the current HSM state and a few important facts just to note down. The first one is that the Lustre HSM command, this is something that we all know about, and just to take a look at it. The facts that the first one is about the Lustre HSM commands, and this involve whole file, that is all the HSM operations which we perform are meant to be performed on the whole file. Sparse files case, again, is delegated to copy tool. If you look at the integration with Lustre HSM coordinator with copy tool, this is done in a way that each HSM operation is expected to be handled by exactly one copy tool instance. The integration follows a loosely coupled model with reference to startup of the copy tool and recovery, where let's say copy tool hangs or crashes for some reason. This is something that is expected to be handled by copy tool. As far as the copy tools itself are considered, the default POSIX copy tool that we are all aware of is limited to POSIX backend and mostly suitable for small files, may not be suitable for large files. There do exist other copy tools, however they are developed for very specific targets and needs. So this is just an overview on the development environment to highlight the problem we're attempting to solve and give a background on the target use case. We're talking about HPC here. So if you look at some very, very specific HPC requirement, it is about archival and restore of a very, very large size file, which can run into petabyte size range. And this is in effectively very less time. So this forms the base requirement for the HSM solution. The HSM solution, as you can see, normally consists of a bunch of data movers and has necessary policy infrastructure for archival of data from primary to secondary archival storage. The primary storage that we have been using is based on Lustre 2.7.0, and this forms the source. Although HSM is about multiple tiers, right? But we're talking about some very specific use case, and that's why we're dealing with primary and secondary storage. Again, just to highlight one important thing is about if we are talking performance again. So we want to extract every bit of features or things that we can make use of. So if here just an example of an archival storage, but if there are certain features that are available on archival storage that can be some of the features can be utilized and just to make it relevant to HSM. So for example, if there are some copy operations which are available within the storage, then that can be utilized to optimize the amount of data that we transferred between the primary and the secondary storage. So, and I'll talk about that in a minute. So, distributed data mover is the core component of HSM solution that we are talking about here. The primary objective is to archive and restore a single large file over multiple nodes in parallel. Besides the primary objectives, there are, of course, other things like performing archival and restore operations on partial file ranges and support all the Lustre HSM operations. And this includes the policy triggered operations. Since we are talking about HPC, this needs to be optimized for performance. And this includes things like throttling, making effective use of available resources, avoiding the need for data transfer, like I mentioned, that if there are some data copy functionality implemented in the secondary storage, then another way to optimize, is to use checksum to just, instead of copying the same amount of data all over again, we can actually initiate a copy operation within the secondary storage to create copies. Besides various tunables to suit one's need for performance. Then reliable archival. This is we're talking about availability and reliability, and reliable archival through for example, checksum, validation of the data that has been archived, recovery from various kinds of failures, controlling the use of resources are some of the examples of integral features of the HSM solution. A quick look at the data mover architecture. The first thing to note is that it follows a peer-to-peer approach where all nodes are considered equal. This means that all the nodes register with Lustre as copy tool, and all nodes participate in data movement. And I'll explain that in some time. The advantage of this approach is that it can scale to a large number of nodes. Besides, there is no single point of failure in the system. Then we follow the plugin based approach, right? Which means that we can attach variety of storage as primary or backend storage. This plugin is normally done through APIs, and API integration offers close integration with storage, and there we can take advantage of this close integration. It can support other file system as HSM tiers. Now, about the I/O. Shared queues are used for managing the I/O request. So all the nodes, this diagram shows 2 nodes, but essentially all nodes are capable of pulling requests from Lustre. And after a node pulls a request from Lustre, it is placed on a shared queue. And so, once it is placed in the shared queue, the other node can pick up this request and process it for I/O. There are multiple threads that are used for I/O, so that essentially takes the advantage of multiple threads as well. All these operations are executed asynchronously. About metadata, so we use shared archival metadata, which can be based on key value store. If the secondary storage again supports the provision to store metadata, then the metadata can be co-located with data, and this is something that helps with DR use cases. A quick overview on the I/O request handling. So this diagram essentially shows how a I/O request is processed over multiple nodes and multiple threads in parallel. So after an I/O request is received from Lustre, it is broken into a set of jobs, as you can see in this diagram. Those jobs are distributed over n nodes, and this distribution essentially follows a pull model. That means any node which has bandwidth can actually pull the request from a shared queue and perform the I/O. Each job essentially contains m individual, basically it contains a few chunks. These chunks, so when it goes to an individual node, the I/O job is broken into chunks, and these chunks can be scheduled over, let's say, k number of threads, or whatever number of threads that are available on the nodes. And finally, a chunk consists of set of buffers, wherein you can have multiple threads doing read and write in parallel. So effectively, if you can see, an I/O request in the best case can actually be done over n into k channels in parallel. This is just to understand it, in a bit more clear. We take an example here. So imagine we have a configuration of buffer size of 32 meg and a buffer count of 1. The chunk size is configured as 4, assuming that we have 2 nodes in this case. A file I/O of request, let's say 256 meg, will be divided into 2 jobs of 128 meg each, and each 128 meg job will be scheduled on each node, where each node will process it using 4 parallel threads of, this is the 4 parallel threads, with each thread doing 32 meg of I/O. This is just to show how requests are handled, monitored, and progress, how the progress is reported back to Lustre about I/O that is happening. So although all nodes are equal, but I've just shown as a classification of originator and data more nodes. So originator node is the node which receives requests from Lustre. And as soon as it receives a request, it actually is transferred to a shared queue, from where another node picks up to handle the I/O. Now, in this case, this request queue is the queue which holds number of requests, and the data mover picks up the request and processes the I/O. It transfers the data. Once the transfer is complete, it actually the response is put back in another queue, response queue, and from where the originator node which placed the request picks it up and remembers it, and it actually passes on the progress and other details back to Lustre. This is just a high-level overview. In reality, it is not that simple. It is much more complex, because we need to handle a variety of failure cases that may happen. So this is just to give a very, very high-level overview on how that happens. The current state of the project, we have V1 available, which is with A200, the Seagate A200 active archival, with limited functionality today, which can transfer single file over single node, but in multiple threads. This is verified to work with Lustre 2.7.0, but what's under development is, and what I just described all about is under development. We do have an internal POC done on the feasibility of that. However, this is something that under development, a lot of work needs to be done still in terms of handling specific failure cases, doing some of the performance optimization that I talked about, for example, zero copy with backend capabilities, integrated metadata for better performance when you do lookup on attributes. So that was the overview on the distributed data mover. Now I'm going to talk about some of the challenges that we faced with Lustre HSM, and then we'll talk about some of the things that we would like to have in the Lustre as a wish list, so that we can make it more relevant to HPC use cases. So the first one is about the copy tool synchronization, and one of the limitation which involves automatic startup of copy tool. So let's say the copy tool was running and something happened, copy tool crashed. And this is something that is administrator or somebody who's administrating the system is needs to handle this. This same is the case with hang. Let's say some HSM action which was in progress and it hanged. This needs to be detected and need to be recovered explicitly. Again, this is one of the limitation. Another limitation is the assumption about HSM operation being handled by one copy tool instance and ability to retry failed operation onto another instance of copy tool. For HSM operations, some of the things is partial file archival and restore, which is a limitation considering the large file use cases. Then restore is performed using volatile file. Volatile file is a file which it doesn't exist in the namespace, but we do have a file handle, and as soon as the file is closed, the file is deleted. Now, one of the problem with volatile file is it is limited on the node on which it was created. So if you want to do restore on multiple nodes, that's a problem. Then there are other issues, minor issues that were faced. So I've just listed it for reference. So based on the issues listed here, here are some of the wish list items which would add a great value to Lustre HSM, keeping in the HPC requirements in mind. I have also given listed down few references of some of the work that is happening, and Andreas did talk about many things that's happening, and that will make this more relevant. The first one is about the archival and restore of partial file, which mainly requires capability to represent a partial file in Lustre. And I think PFL and the file FLR will prove to be very promising in doing this thing. Similarly, FLOCATE can offer the punch hole so that we can actually work on a partial file range for archival, release, and restore. Then multi-node HSM operation would add a lot of value with ability to fail over an HSM action to another copy tool instance if one of the instances is not able to perform. Restore can use multiple volatile streams in each of the participating node. Few other nice to have things is like, for example, special file handling for sparse files, so that policy engine or Robinhood engine can detect and can exclude them altogether from archiving, or can take some granular actions. As far as reliability and consistency is concerned, copy tool channel can help in synchronization with Lustre by receiving more relevant events from Lustre, such as file system restart or client or let's say mount, file system unmount or mount, so that it can take specific actions. Similarly, this is about from Lustre to copy tool. There can be heartbeats from copy tool to Lustre to keep track of copy tool state, so that in case copy tool crashes or hangs, necessary actions can be taken in terms of restarting or maybe rescheduling the HSM action on other copy tool instance. Retry of HSM action is another thing. There is a provision for that already in the code. However, either it is not working or it is yet to be implemented. So another area is the consistency. We're talking large files here, and for large files, I/O can take a very long time, and hence consistency may be an issue because of the larger transfer window. So there can be additions in terms of locking or checkpointing, in terms of some APIs available to copy tool, so that copy tool can take benefit of that. Meaning, whenever it actually performs I/O, it can it can obtain logs or do some checkpointing. So, summary. Just to summarize, we reviewed HSM requirements originating from HPC world. We validated readiness of Lustre with reference to these requirements. We talked about distributed data mover, along with the improvements, some of the improvement suggestions in Lustre that can prove to be promising, for HPC use cases and targeting the needs of HPC. We examined few limitations with Lustre in implementing the HSM solution for HPC, and corresponding solutions or some of the things as wish list that can make help with the Lustre HSM functionality. So this concludes this talk. You can take questions.
Hi, interesting talk. I look forward to seeing how that works out on the distributed mover. I just wanted to point out that a volatile file can be opened on another node or another process. You just use the FID. You can open by FID.
I'm sorry, I cannot hear you.
The volatile file you can open by FID, so you can open that on another node or another process. That's what Lemur does.
I'm sorry, I am not able to hear you clearly. Can you please be more louder? Probably.
Sure. The volatile file, you can open it by FID on a different node.
I'm sorry, I'm really sorry, I'm not able to hear you.
I'll just tell you later.
Maybe we can take it offline and right after this talk, yeah.
Any other questions?
You talked about the shared queue. Is that maintained by a particular instance of the copy tool, or I don't remember seeing where exactly that was being maintained in your architecture?
So we have a subsystem, the communication subsystem, which is taking care of this. Currently, this subsystem is implemented with the use of AMQP protocol. We use RabbitMQ server for that. But this can be, we can just switch over to some other implementation which offers shared queue infrastructure.
Any other questions?